Saturn has 146 known moons. Only one of them orbits the wrong way. While every major moon circles Saturn in the same direction the planet spins, one small world moves against the flow, as though it never belonged there in the first place. Its name is Phoebe. Its chemistry does not match Saturn's family of moons. Instead, it matches frozen objects from beyond Neptune, billions of kilometers farther from the Sun than Saturn itself. When NASA's Cassini spacecraft swept past Phoebe in June 2004, scientists expected to find little more than a battered, captured rock. They did not. The data revealed the fingerprints of a world that had begun an entirely different journey before that journey was violently interrupted. Why does Phoebe orbit backwards when almost nothing else of its size in the Saturn system does? Why does its composition match some of the oldest and coldest objects in the solar system instead of the planet it circles today? What process had already begun inside this tiny world? A process that might eventually have transformed it into something far larger than a moon. What catastrophic event hurled it across billions of kilometers before Saturn's gravity claimed it? And what invisible role has Phoebe been playing throughout the Saturn system for billions of years? One that astronomers did not uncover until 2009. Phoebe is not simply another moon. It is evidence that the solar system we see today is not the solar system that first formed. Before we go any further, if you enjoy exploring the cosmos with us, a quick like or subscribe goes a long way. It helps us keep making these deep dives for curious minds like yours. Let's start with what separates a moon from a planet, because Phoebe's story begins long before Saturn ever captured it. Imagine holding a handful of dust beneath a sky that has not yet settled into familiar worlds. Every grain carries possibility. Every fragment drifts through a young solar system where nothing has claimed its final place. As we continue this journey together, you begin to see that the difference between a moon and a planet was once far less certain than it appears today. Planetary scientists use the word planetesimal to describe one of those early building blocks. A planetesimal is a rocky or icy body created as tiny particles of dust and frozen material repeatedly collided and stuck together. Each successful collision added another thin layer. Growth came slowly, then steadily, as gravity strengthened its hold. This gradual process is called accretion, meaning the continual gathering of surrounding material into something larger over immense spans of time. No planet appeared fully formed. Every familiar world began as countless planetesimals meeting, breaking apart, merging again, and repeating that cycle across millions of years. Some objects gathered enough mass for gravity to dominate their surroundings. Others remained trapped between growth and destruction. Small differences in timing or location often shaped completely different destinies. The young solar system offered little stability. Instead, it resembled an enormous rotating disk filled with gas, dust, rock, and ice, where collisions happened constantly. Some impacts gently expanded growing worlds, others shattered them into fresh debris that became the seeds of future bodies. Chance played a larger role than we often imagine, and every encounter carried lasting consequences. Far beyond Neptune lay the Kuiper Belt, a vast population of icy worlds occupying the distant frontier of the solar system. There, sunlight weakened, temperatures remained extremely low, and material collected at a slower pace than it did nearer the sun. Phoebe formed within this remote environment, surrounded by neighbors, following similar paths of gradual growth. But those distant objects had not finished developing. Many continued accumulating fresh layers, while the architecture of the solar system itself began changing. Massive planets shifted under powerful gravitational influences, disturbing countless smaller worlds. The opportunities that had once encouraged steady growth suddenly disappeared, leaving many developing bodies stranded before reaching their full potential. Phoebe belongs to the family known as Kuiper Belt objects, meaning worlds that originated within that distant icy region. Yet Phoebe no longer lives there. At some point during the solar system's turbulent past, it was removed from its birthplace and eventually settled into orbit around Saturn, almost 1,400,000,000 kilometers, which is about 870 million miles from the giant planet itself. That extraordinary relocation transformed its future forever. As we look at Phoebe today, we are not simply examining another moon circling a distant world. We are studying an unfinished chapter of planetary formation. How much had Phoebe already become before its journey changed? And how much larger might it have grown if the solar system had unfolded just a little differently? Those questions remain at the heart of everything that follows. Far beyond the familiar paths of the giant planets, the solar system opens into a realm that many people never picture. Here, distance changes everything. Sunlight weakens into a pale glow, warmth fades almost completely, and time itself seems to stretch across longer rhythms. We have arrived at the Kuiper Belt, a broad population of ancient icy worlds that preserves some of the earliest chapters of planetary history. Its inner boundary begins around 30 astronomical units from the Sun. An astronomical unit is the average distance between Earth and the Sun, about 150 million kilometers, which is about 93 million miles. From there, the Kuiper Belt extends to roughly 50 astronomical units, reaching almost 7,500,000,000 kilometers. That is nearly 4,660,000,000 miles from the Sun. Across that enormous span lies an astonishing collection of frozen survivors. Astronomers estimate that this region contains hundreds of thousands of objects larger than 100 kilometers, which is about 62 miles. Beyond those larger bodies are possibly trillions of smaller fragments, each tracing its own path through this distant frontier. The Kuiper Belt is far from empty. It is a vast community shaped by gravity, chemistry, and the lingering memory of the young solar system. Among its residents, Pluto remains the most familiar, measuring about 2,377 kilometers across, which is about 1,477 miles. It circles the Sun with 5 known moons. Another remarkable resident is Eris. Although slightly smaller than Pluto in volume, it contains more mass, and its discovery in 2006 encouraged astronomers to redefine what qualifies as a planet. That decision reshaped planetary science across the world. Phoebe began its existence among these distant neighbors roughly 4,500,000,000 years ago. At that stage, it shared the same environment, the same slow pace of growth, and the same reservoir of frozen material surrounding countless developing worlds. But the conditions here differed profoundly from those closer to the Sun. Temperatures remained extremely low, allowing substances such as methane, carbon monoxide, and water ice to remain frozen for immense periods. Rocky minerals existed as well, although in much smaller proportions than within the warmer inner solar system. Those chemical ingredients became part of every collision, every layer, and every stage of gradual growth. That ancient recipe still survives. When the National Aeronautics and Space Administration spacecraft Cassini examined Phoebe during its flyby in 2004, its instruments detected the same chemical fingerprint expected from objects born in the Kuiper Belt. The match proved remarkably strong, leaving little doubt about Phoebe's birthplace. But the contrast reaches beyond chemistry alone. While the inner solar system built worlds through frequent collisions and comparatively rapid accumulation, This distant region advanced at a gentler pace. Material gathered gradually across immense stretches of time, allowing many worlds to remain suspended between humble beginnings and planetary ambition. For more than a century, Phoebe remained little more than a faint point of light drifting across astronomical photographs. Even the largest telescopes on Earth could reveal almost nothing beyond its motion and its unusual orbit. Its surface, its shape, and its history all remained hidden behind distance. We knew it existed, yet we had almost no idea what kind of world it truly was. Everything changed on the 11th of June, 2004. During its long voyage through the Saturn system, the National Aeronautics and Space Administration spacecraft Cassini passed only about 2,068 kilometers above Phoebe's surface, which is about 1,285 miles. No spacecraft had ever approached this distant moon so closely. As the images streamed home, a forgotten object suddenly became a landscape with scars, cliffs, and remarkable detail. The first surprise was its appearance. Instead of a smooth frozen sphere, Phoebe revealed itself as a battered world, covered with craters of every size. Some regions appeared almost as dark as coal, while neighboring areas reflected far more sunlight because bright ice had been exposed beneath the surface. This striking patchwork hinted that Phoebe had experienced a long and complicated history rather than remaining unchanged since its birth. Measurements showed that Phoebe averages about 213 kilometers across, which is about 132 miles. Its actual dimensions measure roughly 218 kilometers by 217 kilometers by 204 kilometers, which are about 135 miles by 135 miles by 127 miles. Gravity had already begun pulling the body toward a rounded shape, although the process never fully reached completion. One feature dominates almost everything around it. The enormous Jason crater stretches about 100 kilometers across, which is about 62 miles, occupying nearly half the width of the entire moon. An impact large enough to carve such a basin came remarkably close to reshaping Phoebe forever. Yet the world survived, preserving the record within its fractured crust. Cassini also revealed layers beneath the surface. Dark material forms an outer coating, while brighter water ice lies underneath, exposed wherever large impacts have broken through the upper layer. Those stacked materials suggest that chemical changes gradually transformed the exterior after Phoebe first formed, leaving older frozen material protected below. Density measurements strengthened that picture. Phoebe has an average density of about 1.63 grams per cubic centimeter, making it denser than pure water ice, which measures about 0.92 grams per cubic centimeter, yet less dense than solid rock. That combination points toward a mixture of ice, rocky material, and carbon-rich compounds assembled long ago. Conditions remain intensely cold today. The average temperature across the sunlit surface reaches about minus 198 degrees Celsius, or minus 324 degrees Fahrenheit. Cassini also detected carbon dioxide, water ice, phyllosilicates, which are clay-like minerals formed through interactions between water and rock, complex organic compounds, and possible cyanide-bearing materials. Together, they revealed a chemistry far more familiar to distant outer solar system bodies than to Saturn's native moons. Imagine standing high above Saturn and watching its family of moons complete their endless circuits. Almost every large moon follows the same graceful direction, moving around the planet the way Saturn itself rotates. That shared motion is called a prograde orbit, meaning an object travels in the same direction as its parent planet's spin. It is exactly what astronomers expect when moons form from the same swirling disk of material that surrounded a growing planet. Then your attention reaches Phoebe. Instead of joining the familiar flow, this small world travels the opposite way. Its path is known as a retrograde orbit, meaning it circles against Saturn's rotation. Phoebe completes one journey around the giant planet in about 550 Earth days, while remaining roughly 12,900,000 kilometers away, which is about 8 million miles. That backward motion immediately separates it from nearly every major moon in the Saturn system. But the direction of travel is only part of the mystery. Phoebe's orbital path is also steeply tilted. Its orbit lies about 175 degrees away from Saturn's equatorial plane, placing it on a dramatically different track from the planet's regular moons. Such an extreme inclination is extraordinarily difficult to explain if Phoebe formed beside Saturn. The contrast becomes even clearer when we compare it with Titan. Saturn's largest moon follows an orbit inclined by less than 0.35 degrees, remaining almost perfectly aligned with Saturn's equator. That close alignment reflects a shared origin inside the disk of gas and dust that once surrounded the young planet. Phoebe displays none of those characteristics. Its motion tells a completely different story. Orbital patterns act like fingerprints. They preserve traces of ancient events long after the objects themselves have changed. When astronomers encounter a large moon moving backward on such a steeply inclined path, they almost always conclude it originated somewhere else before arriving in its present home. Phoebe fits that pattern with remarkable precision. But reaching Saturn was only the beginning. Passing near a giant planet does not automatically produce a permanent moon. An incoming object normally swings around the planet and escapes back into space unless it loses enough speed during the encounter. This process is called gravitational capture, meaning a wandering body surrenders enough orbital energy to remain permanently bound. Several pathways can make that possible. A developing planet may once have possessed an extended cloud of gas that slowed incoming objects through gentle drag. Strong gravitational interactions with other moons could also remove energy from the visitor. Another possibility involves three bodies interacting simultaneously, allowing one object to lose energy while the others carry it away. Each mechanism changes motion in slightly different ways, yet all can transform a traveler into a lasting satellite. Scientists continue examining which pathway best explains Phoebe's arrival, but the evidence carried within its unusual orbit points firmly toward one conclusion. Whatever happened during those distant ages, Phoebe did not begin life as one of Saturn's native moons. It entered from elsewhere, and Saturn never let it leave. The arrangement we see today feels permanent. Jupiter stands beyond the asteroid belt, Saturn follows farther outward, and Uranus and Neptune mark the frozen edge of the giant planets. Yet this familiar order is only the latest version of a much older story. Modern planetary science has revealed that the outer solar system was once arranged very differently, and understanding Phoebe requires us to revisit that forgotten era. In 2005, researchers Alessandro Morbidelli, Harold Levison, and Cleomenes Tsiganis, together with their colleagues, introduced a powerful explanation known as the Nice model. The name comes from the French city of Nice, where the work was developed. Rather than treating the planets as permanent fixtures, this model describes them as restless worlds whose changing orbits reshaped the entire solar system. According to this picture, Jupiter and Saturn originally formed much closer together than they are today. Uranus and Neptune also occupied orbits significantly nearer to the Sunday. The giant planets gradually shifted as they exchanged momentum with countless smaller icy bodies surrounding them, For millions of years, those changes unfolded gradually, but the balance could not last forever. At some point, between about 4 billion, 100 million, and 3 billion, 800 million years ago, Jupiter and Saturn entered a 1 to 2 orbital resonance. An orbital resonance is a repeating gravitational relationship between two bodies. In this case, Jupiter completed exactly 2 trips around the Sun for every single orbit completed by Saturn. That regular rhythm repeatedly strengthened their gravitational influence on one another until the outer solar system became dynamically unstable. But instability on this scale does not remain confined. Powerful gravitational interactions spread outward like expanding ripples. Uranus and Neptune migrated toward the distant frontier, where we find them today. Along the way, they scattered enormous numbers of Kuiper Belt objects inward, transforming orderly populations into wandering travelers crossing the paths of planets. Many of those displaced bodies entered the inner solar system. Their impacts struck Mercury, Earth, the Moon, and other rocky worlds during an interval known as the Late Heavy Bombardment. This name describes a prolonged period when collisions became dramatically more frequent than before. Even now, the heavily cratered surfaces of Mercury and Earth's moon preserve that violent chapter as a geological archive stretching back billions of years. Among the countless objects caught in that upheaval was almost certainly Phoebe. Rather than remaining within its birthplace, it joined the Great Migration triggered by the changing giant planets. Its journey no longer followed the slow pace of gradual growth. Instead, gravity repeatedly redirected its course across immense distances until it wandered into Saturn's domain. But Phoebe avoided the fate that ended many similar worlds. It was neither destroyed nor cast permanently into interstellar space. Instead, this former Kuiper Belt object survived the chaos, becoming one of the rare preserved witnesses to an event that reorganized nearly every corner of the young solar system, while carrying within it a record of the world that existed before everything changed. Growth rarely announces itself. It unfolds through countless small additions, each almost impossible to notice on its own. Across the distant reaches where Phoebe first formed, tiny fragments of ice and rock drifted together, collided gently, and remained connected. Given enough time, those modest encounters slowly built something far greater than scattered debris. Long before the solar system experienced its great gravitational upheaval, Phoebe was actively increasing in size. The process remained much slower than it was closer to the Sun, where denser clouds of material encouraged faster planetary growth. Even so, hundreds of millions of years allowed layer after layer of frozen and rocky material to settle onto Phoebe's surface. Each successful collision left behind another piece of its developing structure. That long history can still be read today. When the National Aeronautics and Space Administration spacecraft Cassini examined Phoebe, it revealed alternating layers of dark organic material resting above brighter water ice. Those stacked layers resemble a geological archive, preserving successive stages of accumulation rather than a single moment of formation. Every exposed cliff and crater wall carries evidence that Phoebe was slowly becoming something more substantial. But growth changes more than appearance. As a world gains mass, its own gravity begins reorganizing the material inside it. Scientists call this process differentiation. Differentiation means heavier, rocky material gradually sinks toward the center, while lighter ice moves closer to the surface. This internal sorting requires enough heat for materials to shift over time, making it an important milestone in planetary development. Phoebe appears to have crossed that threshold. Its average density, measures about 1.63 grams per cubic centimeter, a value suggesting more than a simple mixture of frozen rubble. Combined with its overall size, that density indicates the interior had likely begun separating into distinct layers. Internal heat had become strong enough to influence its structure, even if only during an early stage of its history. At roughly 213 kilometers across, which is about 132 miles, Phoebe occupies an intriguing position among small worlds. It sits near the lower limit where differentiation begins to occur within icy bodies. That makes it especially valuable to planetary scientists because it captures a stage rarely observed directly. We are looking at a world standing near the boundary between a loosely assembled object and one capable of more complex geological evolution. A useful comparison comes from Ceres, the largest body in the asteroid belt. Ceres measures about 940 kilometers across, which is about 584 miles, and has long been recognized as a differentiated dwarf planet. Phoebe never reached that scale, yet the underlying processes appear surprisingly similar. The difference lies mostly in timing and opportunity. But imagine a different history. If the giant planets had never scattered Phoebe from its birthplace, continued accretion across another billion years might have produced a substantially larger world. Its layered interior could have become more complete, geological activity more extensive, and its final identity far closer to that of a dwarf planet than the captured moon we observe today. Long after landscapes have been reshaped and orbits have changed, chemistry continues telling the truth. Every mineral, every frozen compound, and every trace of ancient material preserves part of a world's history. If we want to know where Phoebe truly came from, we need only examine the substances locked within its surface. During the close flyby, one of the most valuable instruments aboard the National Aeronautics and Space Administration spacecraft Cassini was the visual and infrared mapping spectrometer. This instrument identified surface materials by measuring the way different compounds absorbed and reflected light across a broad range of wavelengths. Every chemical leaves a distinctive pattern, almost like a fingerprint, allowing scientists to recognize materials from millions of kilometers away, which is about hundreds of thousands to millions of miles, depending on the observation distance. The results proved remarkable. The instrument detected water ice, frozen carbon dioxide, phyllosilicates, which are clay-like minerals, iron-bearing minerals, complex organic compounds, including possible polycyclic aromatic hydrocarbons, and traces of materials that may contain hydrogen cyanide. Individually, none of these discoveries would have been extraordinary. Together, they painted an unmistakable picture. But that particular combination does not resemble the chemistry of Saturn's regular moons. Instead, it closely matches the compositions measured on distant trans-Neptunian objects, meaning worlds that orbit beyond Neptune, along with centaurs, which are unstable bodies traveling between the giant planets and the frozen nuclei of comets. All of these populations share origins in the remote outer solar system, where lower temperatures preserved compounds that could not easily survive closer to the Sunday. The comparison becomes even stronger when we look inward toward Saturn's native satellites. Enceladus and Mimas, formed within Saturn's own neighborhood and consist primarily of water ice with comparatively simple chemical compositions. Their surfaces reflect the cleaner environment in which they developed. Phoebe carries a far richer chemical inventory, one shaped by conditions that existed much farther from the Sun than Saturn itself. Carbon-rich material is especially revealing. Dark organic compounds cover much of Phoebe's surface, resembling the chemistry commonly found on distant icy bodies. Within the inner Saturn system, energetic radiation and other surface processes gradually alter or remove many carbon bearing compounds across immense spans of time. Phoebe still preserves them in abundance, strengthening the evidence that it spent most of its existence far from Saturn before arriving there. Among the most intriguing discoveries were the phyllosilicates. These minerals form when liquid water reacts chemically with rock over extended periods. Their presence suggests that Phoebe did not remain frozen throughout its entire history. At some early stage, warmth inside the moon allowed water to exist in liquid form long enough to alter its rocky material through chemical reactions. But chemistry rarely forgets. Even after billions of years, those altered minerals remain embedded within Phoebe's crust. They preserve evidence of an ancient interior that was once warmer, more active, and more complex than its cold surface would ever suggest. Every spectral signature collected by Cassini pointed toward the same conclusion, confirming that Phoebe still carries the chemical memory of the distant frontier where its remarkable story first began. A frozen surface can be misleading. From a great distance, Phoebe appears to be little more than an icy body preserved by the deep cold of the outer solar system. Yet, appearances capture only the present. Beneath that ancient crust lies evidence that this small world once experienced conditions very different from those we observe today. Phoebe measures only about 213 kilometers across, which is about 132 miles. At first glance, it seems far too small and far too distant from the sun to have ever contained liquid water, but the source of its warmth did not come from sunlight. It came from within during the earliest chapter of the solar system's history. When the solar system formed roughly 4,567,000,000 years ago, the cloud of gas and dust that gave birth to the planets also contained unstable radioactive isotopes. Radioactive isotopes are atoms with unstable nuclei that naturally release energy as they transform into more stable forms. Among the most important were aluminum-26 and iron-60. These isotopes decayed rapidly over only the first tens of millions of years, releasing heat throughout the bodies that trapped them. Timing became everything. Worlds that formed early enough incorporated significant amounts of these radioactive materials before they disappeared. As the isotopes released energy, temperatures deep inside many young objects steadily increased. In larger bodies, that heat became sufficient to melt internal ice, separate materials by density, and reshape the interior long before the surface revealed any obvious change. Phoebe appears to have formed early enough to receive that hidden source of energy. Computer models reconstructing its thermal history suggest that its interior may have warmed beyond 0 degrees Celsius or 32 degrees Fahrenheit during its earliest tens of millions of years. That threshold allowed ice buried beneath the surface to melt into liquid water, creating conditions capable of driving chemical reactions throughout the rocky interior. But liquid water does more than occupy empty spaces. It becomes an active participant in geology. As warm water circulates through fractured rock, it dissolves minerals, transports dissolved materials, and creates entirely new compounds. This process, known as hydrothermal chemistry, simply means chemical reactions powered by heated water moving through rock. Over time, those reactions alter the composition of the surrounding material in lasting ways. The evidence remains preserved today. Among the minerals detected by the National Aeronautics and Space Administration spacecraft Cassini were phyllosilicates, clay-like minerals that form through prolonged contact between liquid water and rock. Their presence records a period when Phoebe's interior supported conditions very different from its present state. Today, the average surface temperature reaches about minus 198 degrees Celsius or minus 324 degrees Fahrenheit. Nothing about that frozen landscape suggests former warmth. But the minerals embedded within Phoebe's crust preserve the memory of an earlier world, one where internal heat briefly transformed ice into flowing water, altered rock through chemistry, and carried this small body another step along the path toward becoming something much larger. Every scar on Phoebe carries a memory. Unlike worlds that renew their landscapes through volcanism, flowing liquids, or shifting crusts, Phoebe has preserved an extraordinary record of impacts stretching back almost to the birth of the solar system. When you look across its battered surface, you are seeing a history book that has remained open for billions of years. Among the images returned by the National Aeronautics and Space Administration spacecraft Cassini were roughly 50 named craters scattered across nearly every visible region. They range from small bowl-shaped depressions less than 1 kilometer wide, which is about zero point 0.6 miles, to the immense Jason crater, measuring about 100 kilometers across, which is about 62 miles. Jason alone spans nearly half the width of the entire moon, preserving the aftermath of a collision powerful enough to reshape much of Phoebe's outer shell. But the craters reveal far more than impact history. Their walls and central peaks expose layers hidden beneath the surface. Many display bright deposits of water ice beneath a much darker outer coating, rich in carbon-bearing material. Those exposed layers agree closely with the chemical patterns identified through earlier spectroscopic observations, reinforcing the picture of a body that accumulated different materials over long periods rather than forming as a single uniform mass. Planetary scientists use another tool to read these landscapes. It is called crater counting, a method that estimates a surface's age by measuring how many impact craters have accumulated across a given area. Older surfaces generally contain more craters because they have remained exposed for longer periods without being erased by geological activity. Phoebe ranks among the oldest preserved landscapes in the Saturn system. Its crater counts indicate that most of its surface has remained largely unchanged for at least 4 billion years. Even so, change never stopped entirely. Several impact basins display evidence of mass wasting, the slow movement of loose material downslope under the pull of gravity. Debris gradually slid from steep crater walls, softened sharp edges, and collected across lower terrain. The process unfolded at an almost unimaginable pace, yet it continued. Cassini also photographed a prominent ridge, sometimes described as a scarp, extending across part of Phoebe's surface. A scarp is a steep break in the landscape where one section stands noticeably higher than another. This feature may preserve stresses created when water inside Phoebe froze and expanded during its ancient warm phase, gently deforming the crust before the interior settled into permanent cold. The pattern of impacts tells another story as well. Many of Phoebe's oldest craters almost certainly formed before Saturn ever claimed this wandering world. They were inherited from its long residence in the distant outer solar system, then carried intact into a completely different neighborhood. But the story did not end with those collisions. Material blasted outward by later impacts escaped Phoebe's weak gravity, beginning a journey that gradually reached far beyond the moon itself. Long after Phoebe itself had revealed its unusual nature, another surprise emerged from the darkness surrounding Saturn. It was not another moon or an unexpected spacecraft image. Instead, astronomers realized they had overlooked an immense structure that had been present all along, hidden simply because it was almost impossible to see with ordinary light. In 2009, a research team led by Ann Verbisser analyzed observations from the National Aeronautics and Space Administration Spitzer Space Telescope and uncovered an enormous ring surrounding Saturn. This vast structure became known as the Phoebe ring. It immediately transformed our understanding of the Saturn system because it dwarfed every ring previously known. The familiar bright rings, spectacular though they appear, occupy only a tiny fraction of the space influenced by this far larger and far fainter companion. The Phoebe ring stretches outward to nearly 300 Saturn radii, roughly 18 million kilometers, which is about 11.2 million miles, from the planet. Vertically, it extends for about 40 Saturn radii, forming a broad cloud rather than a sharply defined band. The scale is difficult to grasp. If Saturn's bright visible rings were reduced to the size of a single sheet of paper, the Phoebe ring would spread across several city blocks in every direction, surrounding that small center with an almost unimaginable halo. But why had nobody seen it before? The answer lies in the nature of its particles. They are incredibly sparse and exceptionally dark, reflecting very little sunlight back toward telescopes. In visible light, the ring almost disappears into space itself. Infrared observations changed everything because they measured the faint heat radiated by the dust grains instead of relying on reflected sunlight. What appeared empty suddenly revealed a colossal structure suspended around the planet. Its source turned out to be remarkably simple. Every impact striking Phoebe launches tiny fragments from the moon's surface. Phoebe's gravity is weak enough that much of this fine debris escapes into surrounding space instead of falling back. Over immense spans of time, sunlight exerts a subtle force called solar radiation pressure, gradually pushing those dust particles inward toward Saturn. The motion is extraordinarily slow, yet it never truly stops. Each collision, therefore, contributes another handful of material to an expanding cloud. Across billions of years, countless impacts have supplied enough dust to create the largest known planetary ring in the solar system. Phoebe has done far more than preserve its own ancient history. It has continuously reshaped the environment around Saturn through an almost invisible stream of escaping debris. The drifting particles also preserve Phoebe's unusual identity. They travel in the same retrograde direction as the moon that released them, carrying the signature of their captured origin across the Saturn system. Eventually, many of those grains cross the orbit of Iapetus, another of Saturn's moons, where their long journey begins to leave marks on an entirely different world. Few worlds reward a careful glance as dramatically as Iapetus. As it circles Saturn, one side gleams with brilliant water ice, while the opposite hemisphere appears astonishingly dark. This contrast is so striking that when Giovanni Cassini observed the moon in 1671, he noticed something deeply puzzling. Iapetus seemed to disappear during part of its orbit, then return again, as though half of the moon had simply vanished from view. For more than 3 centuries, astronomers searched for an explanation. They proposed differences in geology, ancient eruptions, and even uneven frost deposition. Each idea accounted for part of the mystery, yet none explained the remarkable sharpness of the boundary separating light from dark. But the answer eventually emerged from a place far beyond Iapetus itself, linking 2 distant worlds through an almost imperceptible exchange of dust. That source is Phoebe. More precisely, it is the stream of microscopic debris that escapes Phoebe after countless impacts and becomes part of the vast outer ring surrounding Saturn. Those tiny grains do not remain suspended forever. Over immense spans of time, sunlight gradually alters their paths, drawing them inward until they cross the orbit of Iapetus. Because Iapetus travels through space like a moving target, the particles strike its leading hemisphere, the side facing forward along its orbital path, far more often than the trailing side. The result has accumulated grain by grain across billions of years. The leading hemisphere, known as Cassini regio, has become coated with dark material rich in carbon compounds that originated on Phoebe. Its reflectivity, known as albedo, measures only about 0.03, meaning it reflects roughly 3% of the sunlight reaching its surface. That makes it one of the darkest known landscapes anywhere in the solar system. But the opposite hemisphere followed a different history. It receives almost none of Phoebe's drifting debris and remains covered largely by bright water ice. Its albedo is about zero point 0.5, allowing it to reflect roughly half of the sunlight that falls upon it. The difference between these neighboring hemispheres is extraordinary. One absorbs warmth efficiently, the other shines brightly back into space. That contrast strengthened itself over time. The darker surface became slightly warmer, causing some ice to sublimate, meaning it changed directly from solid into vapor without first becoming liquid. The escaping water later condensed onto colder, brighter regions, increasing the contrast even further. A modest coating of imported dust gradually reshaped the appearance of an entire moon. Phoebe never collided with Iapetus. It never passed close enough to carve valleys or raise mountains. Yet across millions of kilometers, which is about 12.4 million miles of open space, it steadily transformed another world through drifting particles too small for the eye to follow. But that delicate exchange reveals something profound. Even in the immense distances between planets and moons, the history of one world can become permanently written onto another. A diameter of 213 kilometers, which is about 132 miles, sounds precise, yet the number alone hides its true significance. Without a point of comparison, you could easily imagine Phoebe as either enormous or insignificant. Planetary science tells a different story, because size alone never determines a world's potential. Mass, gravity, composition, and history all become part of the same equation. Our own moon measures about 3,474 kilometers across, which is about 2,159 miles. That makes it more than 16 times wider than Phoebe. But the difference extends far beyond appearance. When the diameter of a world doubles, its volume grows by roughly 8 times, provided the overall shape remains similar. That increase means substantially more material, stronger gravity, and a much greater ability to reshape itself from the inside. Gravity changes everything. As a growing body becomes more massive, its own weight begins pulling equally from every direction. Sharp edges gradually soften, deep depressions become less pronounced, and the entire object slowly relaxes toward a rounded form. Planetary scientists call this condition hydrostatic equilibrium, meaning gravity has become strong enough for a body to assume an approximately spherical shape. It represents one of the defining characteristics used by the International Astronomical Union when identifying a dwarf planet. Phoebe occupies an especially intriguing position near this boundary. Cassini revealed a world that is not perfectly spherical, yet it is noticeably rounded rather than irregular. That shape suggests gravity had already begun overcoming the strength of its icy and rocky materials before its growth came to an end. The transformation had started. It simply never reached completion. Comparison with other moons reinforces this picture. Mimas, another satellite of Saturn, measures about 396 kilometers across, which is about 246 miles. It is generally regarded as lying near the lower limit, where a water ice body can reliably achieve hydrostatic equilibrium. But Phoebe differs in an important way. Its density is considerably higher because it contains a larger proportion of rocky material mixed with ice. Denser materials respond differently to gravity, meaning the exact threshold for becoming rounded does not remain identical from one object to another. That distinction makes Phoebe more compelling than its modest dimensions first suggest. It had already begun following a developmental path toward greater internal complexity before events beyond its control interrupted that progress. Continued accumulation inside the distant Kuiper Belt could eventually have increased its diameter into the range of roughly 500 kilometers, which is about 311 miles, to 1,000 kilometers, that is nearly 621 miles. At that scale, gravity would almost certainly have completed the rounding process, supporting richer geology, a more evolved interior, and perhaps even a long-lived internal ocean. But history redirected Phoebe before it reached that future, leaving us with a world preserved at the edge of planetary possibility. Imagine following Phoebe through an era when no stable destination existed. Instead of belonging to any planet, it wandered between giants, moving through a region where every close encounter could redirect its future. You travel beside a world that has already left its birthplace behind, yet has not reached the system that will eventually claim it. This was the stage planetary scientists describe as the centaur phase. A centaur is a small body traveling in an orbit that crosses or approaches the paths of the giant planets. Such an orbit is naturally unstable because each close pass allows gravity to reshape the object's course. Jupiter, Saturn, Uranus, and Neptune continually tug these travelers in different directions. Over time, even small changes accumulate into dramatic shifts. Calculations suggest that most centaurs survive in this state for only a few million years before being ejected from the solar system, drawn inward toward the inner planets, or permanently captured by a larger world. We can still observe members of this restless population today. Chiron measures about 200 kilometers across, which is about 124 miles, and has displayed activity resembling that of a comet as frozen materials escape into space. Chariklo is about 250 kilometers across, which is about 155 miles, and surprised astronomers by becoming the first known minor planet discovered to possess its own ring system. Another well-studied example, Pholis, carries an unusually dark and chemically rich surface that preserves compounds from the distant outer solar system. These surviving centaurs provide valuable clues about Phoebe's forgotten journey. During its migration, sunlight gradually became more intense than it had been in the distant Kuiper Belt. The increase remained modest compared with conditions near Earth, yet it was enough to affect fragile frozen materials trapped beneath the surface. But the transformation unfolded slowly, allowing chemistry to respond over extended periods rather than in sudden bursts. Some researchers propose that this warming triggered episodes of outgassing. Outgassing is the release of gases as frozen volatile materials change directly into vapor without becoming liquid first. Compounds such as carbon dioxide and methane may have escaped through fractures or porous layers, carrying fine dust into the surrounding space. If that happened, Phoebe could briefly have worn a faint coma, a diffuse cloud of gas and dust surrounding an active icy body, making it resemble a subdued comet before the activity faded once more. Every encounter narrowed the possibilities. A slight change in speed or direction during one passage could determine the next destination. Most centaurs eventually disappear from their wandering paths through collision, escape, or continued migration, but Phoebe experienced a rarer outcome. It passed close enough to Saturn for the planet's gravity to hold it, ending millions of years of uncertainty. From that moment onward, its identity changed forever, preserving within a captured moon the history of an ancient traveler that once belonged to no planet at all. Every journey through the solar system eventually meets a crossroads where motion alone is no longer enough. For Phoebe, that decisive passage came during a close encounter with Saturn, when a wandering world approached a planet whose gravity was powerful enough to change its future forever. But gravity alone could never guarantee capture. A body arriving from interplanetary space carries tremendous orbital energy. Unless some of that energy is removed, the visitor follows an open path called a hyperbolic trajectory, meaning it bends around the planet once before escaping back into space. The encounter can be dramatic, yet it remains temporary. To become a permanent moon, Phoebe needed its speed to fall just enough for Saturn's gravity to transform that fleeting passage into a bound orbit. Planetary scientists continue to investigate exactly how this happened. One leading explanation involves the Proto-Saturnian Nebula, a broad disk of gas surrounding Saturn during the earliest stages of its formation. As Phoebe traveled through this extended envelope, friction with the gas could have reduced its speed by a small but crucial amount. The change would not have needed to be large. Even a modest loss of orbital energy could have converted an escape path into an elongated orbit around Saturn. But that opportunity would have existed only briefly. The gas surrounding young Saturn gradually dispersed into space, leaving a much cleaner environment behind. Once that happened, gas drag could no longer assist incoming objects. Any capture through this process had to occur during a relatively early chapter in Saturn's history. Another possibility involves a three-body gravitational interaction, where Saturn, Phoebe, and another substantial object exchanged energy during a close encounter. In simple terms, gravity acted like a moving balance, allowing one participant to gain energy while another lost it. Phoebe may have surrendered enough motion during such an encounter to remain with Saturn, while the other body departed on a different course. But there is also a broader explanation that connects naturally with the earlier upheaval across the outer solar system. During the period described by the Nice model, countless bodies crossed one another's paths while the giant planets shifted into new orbits. That chaotic environment greatly increased the chances of unusual gravitational encounters, making permanent captures more likely than they would be in today's comparatively settled solar system. The evidence preserved around Saturn supports the idea that Phoebe was not the only traveler caught during this era. The planet possesses about 100 irregular moons, distant companions, following inclined and frequently retrograde paths that differ sharply from the orderly orbits of moons formed beside Saturn. Together they resemble a collection assembled from many separate arrivals rather than a single family born in place. Phoebe stands apart even within that remarkable group. It is roughly 8 times larger than Saturn's next largest irregular moon, suggesting it was among the earliest, most substantial, or most fortunate objects ever claimed by the planet's immense gravitational reach. Step farther from Saturn, and the scene becomes unexpectedly crowded. Phoebe appears at first to be an isolated traveler circling far beyond the familiar major moons. But careful observation reveals that it is surrounded by companions following remarkably similar paths. Together, they tell the story of a shared past, written not through formation, but through fragmentation. Planetary scientists refer to this collection as the Phoebe group, It includes dozens of small, irregular moons, many of which remain unnamed because of their modest sizes and distant orbits. Most measure only a few kilometers across, which is about a few miles across, while others reach several tens of kilometers, that is nearly several dozen miles. Although each follows its own orbit, their shared retrograde motion, comparable orbital inclinations, and similar distances from Saturn point toward a common ancestor. That ancestor is almost certainly Phoebe itself. During the violent era, when impacts were frequent throughout the outer solar system, large projectiles repeatedly struck its surface. Some collisions excavated enormous quantities of rock and ice with enough speed to escape Phoebe's weak gravity while remaining trapped by Saturn. Instead of falling back, those fragments entered independent orbits and gradually became moons in their own right. But these scattered remnants did not drift randomly. Their orbital clustering is unusually consistent, allowing specialists in orbital dynamics, scientists who reconstruct past events from the motions of celestial bodies, to trace their histories backward through mathematical simulations. Those calculations indicate that many of the family forming collisions occurred during the same broad period associated with the late heavy bombardment, when impacts reshaped countless worlds across the solar system. Phoebe therefore occupies an unusual place within Saturn's collection of satellites. It is more than another captured moon. It became the parent body of an entire outer family whose members preserve the consequences of ancient collisions across billions of years. Each small satellite serves as another surviving fragment of a much larger history. The debris produced during those impacts did not all remain as solid moons. Some material broke into much finer particles that continued orbiting Saturn instead of gathering into larger bodies. Over immense spans of time, repeated collisions supplied additional dust to the vast diffuse structure already surrounding the planet. But this continual exchange means the Phoebe ring is not simply the product of one object. It also carries contributions from pieces that once belonged to Phoebe before becoming independent worlds. Imagine Saturn without that single capture. The Phoebe group would never have formed because its parent body would have remained far beyond Neptune. The immense dust ring would also be absent. Without that supply of dark material drifting inward, Iapetus would retain a dramatically different appearance. One captured traveler therefore reshaped an entire region of the Saturnian system, leaving behind descendants, dust, and lasting connections that continue to define the planet's distant frontier. Some discoveries depend on decades of observation. Others arrive in a single passing moment. Phoebe revealed most of its secrets during an encounter so brief that, measured against the lifetime of the solar system, it was scarcely more than an instant. Yet everything we have explored since traces back to those precious hours. The Cassini spacecraft reached Saturn in the year 2004 after a journey lasting nearly 7 years. Before settling into orbit around the giant planet, mission planners directed the spacecraft toward Phoebe for its only close encounter. On the 11th of June, 2004, Cassini swept past the distant moon, gathering information continuously for roughly 6 hours. There would never be another opportunity during the mission to return. But the encounter unfolded at extraordinary speed. Relative to Phoebe, Cassini traveled at about 6.1 kilometers each second, which is about 3.8 miles each second. At that pace, the spacecraft could have crossed the average distance between Earth and the Moon in roughly 1 minute. Every instrument, therefore, had only moments to record measurements before the geometry changed forever. The reward was remarkable. During those 6 hours, Cassini gathered more scientific information about Phoebe than astronomers had accumulated since its discovery in the year 1899. Decades of distant observations were suddenly replaced by close examination, transforming an obscure point of light into a richly detailed world with its own geological history. The imaging science subsystem recorded photographs at resolutions reaching about 12 meters for every picture element, which is about 39 feet for every picture element. Features that had once blended together became individual cliffs, crater walls, bright ice exposures, and scattered boulders resting across the ancient terrain. We could finally study the moon as a landscape instead of a distant object. Other instruments added layers that ordinary images could never provide. The composite infrared spectrometer measured the heat naturally emitted from Phoebe, allowing scientists to reconstruct aspects of its thermal evolution over billions of years. Those observations strengthened the evidence that the interior had once been considerably warmer than its frozen surface suggests today. But Cassini also performed an experiment without touching the moon at all. As the spacecraft rushed past, Phoebe's gravity altered its path by an almost imperceptible amount. The radio science subsystem measured those minute changes with extraordinary precision. From that information, researchers calculated Phoebe's mass to be about 8.29 quintillion kilograms, providing one of the key values needed to determine its density and internal structure. Every major conclusion about Phoebe's composition, origin, geology, chemistry, and evolution rests primarily upon that single encounter. Cassini continued exploring Saturn until its mission concluded in the year 2017, ending with its deliberate descent into the planet. But the understanding we now possess of this captured traveler was secured during one 6-hour passage, a fleeting conversation between spacecraft and moon that forever changed how we see Saturn's distant frontier. Imagine placing Phoebe beside another traveler born from the same distant nursery. Their earliest ingredients were remarkably alike, gathered from the cold outskirts of the young solar system at nearly the same time. Yet from those similar beginnings, their histories separated until they became almost unrecognizable relatives. Pluto grew into a world measuring about 2,377 kilometers across, which is about 1,477 miles. Phoebe reached only about 213 kilometers across, which is about 132 miles. That difference appears modest when spoken aloud. In planetary science, however, a larger diameter represents an enormous increase in volume, mass, and gravitational strength. Every additional layer of material gave Pluto greater ability to attract still more matter from its surroundings. As Pluto continued growing, gravity reshaped its interior and surface across billions of years. The New Horizons spacecraft revealed mountains of water ice rising roughly 3,500 meters, which is about 11,482 feet. Vast frozen plains spread across regions such as Tomball Regio, a broad basin filled mainly with nitrogen ice. Scientists also identified towering features that may be cryovolcanoes, meaning volcanoes that erupt water, ammonia, or other frozen compounds instead of molten rock. Above all this rests a thin atmosphere composed primarily of nitrogen and methane, changing gradually as Pluto moves around the Sunday. But Phoebe followed another path. Its growth slowed before it could reach comparable size. Without sufficient mass, many geological processes remained limited, even though earlier evidence shows its interior once experienced warmth and chemical transformation. The difference between these worlds, therefore, reflects accumulated material as much as passing time. One object continued building, the other was interrupted. Their later histories widened the contrast. Pluto remained within the distant belt, where countless icy bodies still orbit beyond Neptune. Phoebe was scattered inward during the era of planetary migration, eventually becoming bound to Saturn instead. That single change altered everything that followed, from its environment to its collisions and long-term evolution. When the New Horizons spacecraft swept past Pluto during the year 2015, scientists finally obtained a detailed portrait of a fully developed Kuiper Belt world. Comparing those observations with Cassini's close examination of Phoebe creates an extraordinary scientific pairing. We are effectively looking at two objects that began with similar raw materials, while fate carried them toward completely different outcomes. But perhaps the most remarkable lesson is how narrow that divide may have been. Had Phoebe remained undisturbed and accumulated even about 20% of the additional mass that Pluto eventually gained, its gravity could have carried it beyond the accepted threshold for a dwarf planet. You would likely see a body with a richer geological history, possible companion moons, perhaps even a delicate atmosphere, standing today beside Pluto as another fully matured survivor from the solar system's distant frontier. Before we notice the scars across Phoebe, we notice something simpler. Light struggles to return from its surface. Even beneath the distant sun, this moon appears remarkably dim, as though it has spent billions of years collecting darkness instead of reflecting daylight back into space. Its average reflectivity, known as albedo, is only about 0.081. In simple terms, Phoebe reflects roughly 8% of the sunlight that reaches it. That makes it substantially darker than most of Saturn's larger moons. Titan reflects around 22% of incoming sunlight, while Enceladus presents an even greater contrast. Fresh ice covering Enceladus reflects so efficiently that its measured albedo exceeds 1, reaching about 1.38 because light scatters repeatedly through its exceptionally bright surface. But Phoebe did not begin with darkness alone. The color comes largely from carbon-bearing material spread across its exterior. Carbon-bearing simply means compounds that contain carbon atoms, many of which formed in the cold outer solar system long before planets settled into their present arrangement. These materials absorb much of the sunlight that strikes them, leaving very little to scatter back toward distant observers. Among those compounds are substances commonly called tholins. These complex organic materials form when simple molecules such as methane and nitrogen are exposed for immense spans of time to ultraviolet sunlight and energetic cosmic rays. Bit by bit, ordinary molecules become larger and chemically richer. The result is a dark coating that blankets many ancient bodies living beyond the orbit of Neptune and survives long after those objects migrate elsewhere. Phoebe shares this appearance with several cometary nuclei. Halley's comet, for example, reflects only about 4% of incoming sunlight, making it one of the darkest known natural surfaces in the solar system. Scientists find that similarity especially meaningful because both bodies appear to preserve related chemical ingredients inherited from the distant regions where they formed. Their surfaces carry the imprint of ancient radiation, rather than recent geological renewal. But darkness changes more than appearance. A surface that absorbs additional sunlight also gains slightly more heat. Even so, Phoebe remains intensely cold. Average surface temperatures stay close to minus 198 degrees Celsius, or minus 324 degrees Fahrenheit. The extra absorbed sunlight raises temperatures only modestly, nowhere near enough to erase the frozen character of this distant world. Cassini revealed the most compelling evidence when impacts pierced that dark covering. Many crater walls and floors expose brilliant deposits of water ice beneath the outer layer, creating dramatic patterns of bright and dark terrain across the landscape. You are seeing two histories at once. The darker coating records billions of years of chemical processing under relentless radiation, while the bright ice beneath preserves material that has changed far less since Phoebe first emerged in the remote frontier of the young solar system. Some worlds become valuable because they are extraordinary. Others become valuable because they preserve a moment that almost vanished. Phoebe belongs to the second kind. Its greatest scientific importance comes from the fact that its long journey changed location without erasing the evidence of where it began. Across the outer reaches of the young solar system, countless icy bodies formed from the same broad reservoir of dust, rock, and frozen gases. Most never became convenient subjects for close investigation. Many were absorbed into growing, giant planets. Others were scattered completely beyond the solar system. Vast numbers still remain in the distant Kuiper Belt, where even our finest telescopes reveal only limited details from billions of kilometers away, which is about billions of miles. But Phoebe followed an uncommon path. After its migration and eventual capture, it entered an environment that a spacecraft could realistically reach. That unlikely sequence allowed the Cassini mission to examine an ancient Kuiper Belt object with remarkable precision. Instead of relying only on reflected light viewed from immense distances, scientists measured its gravity, mapped its geology, analyzed its minerals, and examined the chemical fingerprints preserved across its surface. Those observations extend far beyond a single moon. Every clue extracted from Phoebe contributes to larger models describing how small worlds accumulated material during the solar system's earliest history. Its layered structure, evidence for internal warming, and mineral transformations all help researchers test competing ideas about planetary accretion, the gradual process through which dust and smaller bodies collide and merge into larger ones. Each result narrows the range of possibilities for conditions that existed more than 4 billion years ago. But the importance grows even wider. Worlds such as Pluto, Eris, Makemake, and Haumea cannot reveal every detail of their interiors through distant observation alone. Scientists compare what they learn from Phoebe with measurements collected across those larger dwarf planets, searching for shared patterns in composition and evolution. Similar comparisons also improve our understanding of centaurs and comets, whose distant or rapidly changing behavior often limits direct investigation. Phoebe therefore serves as a calibration anchor. In astronomy, a calibration anchor is an object studied well enough that its measured properties help scientists interpret observations of similar bodies located much farther away. When telescopes detect familiar spectral signatures, meaning distinctive patterns of absorbed and reflected light, researchers can compare those patterns with Phoebe's known chemistry to reach more reliable conclusions about worlds they may never visit directly. But perhaps the deepest lesson is wonderfully simple. You and we are not looking only at a captured moon circling Saturn. We are examining preserved material from the earliest chapter of planetary construction, carried inward across the solar system and placed within humanity's reach. Phoebe transformed from an overlooked satellite into one of the clearest surviving records of how distant worlds first began to form, grow, and change before the architecture of the solar system settled into the arrangement we recognize today. Nothing that circles Saturn remains perfectly fixed forever. Every orbit changes, even when those changes unfold so gradually that countless generations of stars seem to pass before the difference becomes noticeable. Phoebe is no exception. Its path continues to evolve beneath the steady influence of gravity, following rhythms measured across immense spans of time. The strongest long-term influence comes from the Sun itself. Although Saturn firmly controls Phoebe's motion, the Sun still exerts a persistent tidal pull across the vast distance separating them. A tidal force is simply the slight difference in gravitational attraction across an object's orbit, and over millions of years, it slowly alters the shape, tilt, and orientation of that orbit. These changes do not happen smoothly every day. They accumulate through repeating cycles that stretch across geological ages. But the Sun is not acting alone. Saturn's many moons also contribute small gravitational nudges whenever their motions align in particular ways. Each individual disturbance is tiny. Together, they gradually reshape the balance that has kept Phoebe circling the giant planet since its capture. Computer simulations suggest that, over hundreds of millions to billions of years, these combined influences may eventually push the orbit toward increasing instability. Several outcomes remain possible. One future sends Phoebe onto a path that escapes Saturn's gravitational hold altogether, allowing it to resume an independent journey around the Sunday. Another possibility draws the moon steadily inward, reducing the distance between Phoebe and Saturn over extraordinary lengths of time. Neither outcome lies anywhere near humanity's future, yet both remain physically plausible according to current models of orbital evolution. If that inward migration eventually became substantial, another force would begin to dominate. Saturn's tides would stretch Phoebe more strongly with every closer passage. Tidal forces arise because the side facing Saturn experiences a slightly stronger gravitational pull than the far side. Over enough time, those stresses could fracture ancient rock, shift buried layers, and perhaps awaken geological activity within a world that has remained largely unchanged for about 4 billion years. But there is a final boundary. Astronomers call it the Roche limit, the distance where a planet's tidal forces become stronger than the gravity holding a smaller body together. Should Phoebe ever cross that threshold, it would no longer survive as a single moon. It would gradually break apart, releasing countless fragments into orbit around Saturn. Those fragments would spread into a new ring, joining the planet's already remarkable collection of orbiting debris. The transformation would complete an astonishing cycle. A body born in the distant Kuiper Belt became a wandering traveler, then a captured moon, and in the far future it may become part of Saturn's rings themselves. You can almost trace the entire history of the solar system through that single, uninterrupted journey, written not in words, but in gravity, ice, rock, and time. Some worlds invite this question through oceans, atmospheres, or active geysers. Phoebe reaches it by a very different path. Today, you would find an airless landscape locked in deep cold, with surface temperatures averaging about minus 198 degrees Celsius or minus 324 degrees Fahrenheit. Sunlight arrives only as a faint remnant after crossing the immense distance to Saturn. Every visible feature suggests a place where life cannot survive. But present conditions tell only part of the story. Planetary science often asks whether a world was once different enough to permit the chemistry that life requires. That distinction matters here. We are not searching for living organisms on modern Phoebe. We are asking whether, during its earliest history, it briefly possessed the ingredients that researchers consider essential for life's beginnings. Those ingredients are surprisingly familiar. Liquid water provides a medium where chemical reactions can proceed. Organic molecules, meaning carbon-bearing compounds capable of forming increasingly complex structures, supply the raw material. An energy source drives those reactions forward. Evidence gathered from Phoebe indicates that all three likely existed together during the moon's youth. Heat came from radioactive decay inside the newly formed body. Certain unstable elements released energy as they naturally transformed into more stable forms. During the first tens of millions of years, that internal warmth appears to have melted buried ice, creating pockets or layers of liquid water beneath the surface. Similar heating is believed to have sustained hidden oceans within worlds such as Enceladus and Europa, although through different combinations of energy sources and geological histories. But warmth alone is never the entire story. Water circulating through rocky material can trigger hydrothermal reactions, meaning chemical exchanges between heated water and minerals. On Earth's ocean floor, comparable environments support thriving ecosystems and remain among the strongest candidates for where life first emerged. Phoebe's rocky interior, combined with abundant organic compounds inherited from the outer solar system, may have allowed similar prebiotic chemistry, the network of reactions that can assemble increasingly complex molecules before life itself appears. The opportunity, however, was remarkably brief. As the short-lived radioactive elements exhausted their energy, the interior gradually cooled. Liquid reservoirs froze once more. Chemical activity slowed until it nearly stopped. The window may have lasted only tens of millions of years, an instant compared with the age of the solar system. That conclusion demands careful restraint. Nothing discovered by the Cassini spacecraft indicates that life ever appeared on Phoebe. No biological signatures have been detected, and none are expected on its frozen surface. But you can see why scientists continue asking the question. Long before Saturn claimed this wandering world, Phoebe briefly possessed liquid water, organic chemistry, and internal energy, the same combination that guides modern investigations into how life might first emerge elsewhere in the universe. Stepping back from Saturn for a moment reveals a broader pattern woven across the solar system. Worlds do not always remain where they formed. Some wandered for immense spans of time before the gravity of a giant planet redirected their futures forever. Phoebe belongs to this remarkable family of captured moons, yet its story remains unusually complete because a spacecraft examined it at close range. The clearest comparison lies around Neptune. Its largest moon, Triton, measures about 2,706 kilometers across, which is about 1,682 miles. Like Phoebe, Triton travels in a retrograde orbit, moving opposite the direction expected for a moon that formed naturally around its planet. That orbital signature strongly indicates capture from the distant outer solar system. But Triton arrived with far greater mass, bringing consequences that reshaped Neptune's entire satellite system. Models of Neptune's history suggest Triton's capture disrupted the planet's original collection of moons through repeated gravitational encounters. Some were likely driven into Neptune itself. Others may have collided with one another or escaped into interplanetary space. A gravitational encounter is a close passage where the pull between bodies dramatically changes their paths. One captured world may therefore have erased much of an older family before settling into its present orbit. Mars presents a different puzzle. Its tiny moons, Phobos and Deimos, resemble dark asteroids in several ways, leading many researchers to consider them captured bodies originating near the outer asteroid belt. But their nearly circular orbits do not perfectly match a simple capture scenario. Alternative ideas propose that both moons formed from debris produced by a giant impact near Mars. The evidence continues to be evaluated, reminding us that planetary history rarely follows a single uncomplicated path. But Saturn is not unique in gathering wandering objects. Jupiter possesses dozens of distant irregular moons organized into orbital families, such as the Ananke group and the Carme group. These collections share similar orbital characteristics, suggesting common origins through capture, followed by ancient collisions that fragmented larger parent bodies. Saturn displays the same broad pattern, with Phoebe standing as the dominant survivor of its own family. Phoebe's importance reaches beyond belonging to this category. At about 213 kilometers across, that is nearly 132 miles, it grew large enough for internal heating to alter its structure early in its history. The Cassini spacecraft directly measured its chemistry, density, and surface composition in extraordinary detail, something unavailable for nearly every other captured moon. But its influence extends even farther. Material escaping from Phoebe created an enormous ring, darkened Iapetus over immense spans of time, and contributed fragments that became additional satellites. Most captured moons simply accompany their planets. Phoebe transformed the system that claimed it. Long before spacecraft crossed Saturn's realm, Phoebe existed only as a faint mark hidden within glass. Its discovery began inside an observatory rather than at the eyepiece of a telescope, marking the arrival of a new way to explore the solar system. Instead of relying solely on what the human eye could detect, astronomers had begun trusting photographic plates, long exposure images capable of preserving light far too faint for direct observation. On the 18th of March, 1899, William Henry Pickering examined photographs taken at the Boyden Station of the Harvard College Observatory in Arequipa, Peru. Each plate recorded thousands of distant stars. Almost every point of light remained fixed from one night to the next, but one tiny speck had shifted slightly across the background. That slow movement revealed something extraordinary. It belonged to the solar system rather than the distant universe beyond. The object was soon confirmed as Saturn's ninth known moon. It also ranked among the faintest and most distant moons known at the time. Even the largest telescopes of the era could reveal almost nothing beyond its existence. There were no visible craters, no clues about its composition, and no hint that this small world had begun its life far beyond Saturn. Astronomers possessed only a moving point of light and the mathematics describing its orbit. But those calculations quickly exposed an unexpected detail. Phoebe traveled around Saturn in a retrograde direction, opposite the motion followed by the planet's major moons. That unusual path immediately suggested that something about its history differed from the familiar satellites orbiting closer to Saturn. Scientists recognized the anomaly, yet they lacked the broader understanding needed to explain it. The Kuiper Belt had not yet been discovered. Modern models describing the early rearrangement of the giant planets remained many decades away. The crucial pieces of the puzzle simply did not exist. Phoebe also achieved another distinction that extended beyond planetary science. It became the first moon ever discovered through photography instead of direct visual observation. That milestone demonstrated how rapidly astronomical techniques were advancing. Glass plates could preserve details impossible to catch during a single glance through a telescope, allowing patient comparison to uncover objects hidden within enormous fields of stars. For the next 105 years, Phoebe resisted every attempt to reveal more. Improved telescopes refined its orbit and estimated its brightness, yet its surface remained unresolved. Scientists debated its nature, using little more than reflected sunlight and careful calculation. The real landscape stayed beyond reach, but everything changed before the Cassini spacecraft entered orbit around Saturn. During a flyby, lasting only about 6 hours, cameras and scientific instruments transformed a century-old mystery into a richly documented world. A tiny moving dot became a place with mountains, impact basins, buried ice, measurable chemistry, and a history stretching back to the birth of the solar system itself. Knowledge sometimes advances by revealing deeper uncertainty. After everything Cassini uncovered, you might expect Phoebe to feel thoroughly understood. Instead, the remarkable success of that brief encounter sharpened a collection of unanswered questions. We now recognize the outlines of its story with far greater confidence. Yet, many important chapters remain blurred because they lie beneath the surface or far beyond the reach of a single passing spacecraft. One enduring mystery concerns the moment Phoebe became part of Saturn's family. Several explanations remain scientifically plausible. One possibility suggests that the young Saturn still possessed a broad envelope of gas, creating enough resistance to slow Phoebe until capture became permanent. Another proposes a three-body interaction, meaning the gravity of multiple objects briefly worked together to rob Phoebe of enough energy for Saturn to retain it. But modern models describing the early migration of the giant planets also provide a convincing path, with widespread gravitational upheaval scattering countless distant worlds into new orbits. Current evidence does not clearly favor one explanation over the others. Its hidden interior presents another challenge. Surface measurements indicate that Phoebe probably experienced differentiation, the process in which warmer material separates into internal layers while an object is still young. Yet probability is not proof. Scientists cannot directly confirm whether a dense rocky core truly exists or determine its exact size and structure from a flyby alone. Resolving that question would likely require a dedicated spacecraft capable of orbiting Phoebe while carrying a gravimetry instrument, which measures tiny changes in gravity to reveal what lies inside. The enormous Jason crater also continues to invite careful investigation. Its immense scale suggests an impact powerful enough to reshape much of the moon. But researchers still debate whether the basin resulted from one colossal collision or from several overlapping impacts spread across time. Another possibility remains intriguing. Did the object that excavated Jason come dangerously close to shattering Phoebe completely? Existing observations cannot provide a definitive answer. But uncertainty extends beyond geology. The precise timing of Phoebe's capture remains unresolved. Was it drawn into Saturn's influence during the period known as the Late Heavy Bombardment before that era began, or after it had largely ended? Each possibility fits different models describing the evolution of the young solar system, making the answer important far beyond Phoebe itself. Even the chemistry beneath the outermost layers remains partly hidden. Cassini sampled exposed material and fresh crater walls, allowing scientists to infer the deeper composition with considerable confidence. Inferred evidence, however, differs from direct measurement. Samples from greater depths could reveal unexpected complexity. For now, no approved or funded mission is preparing to return. Exploration priorities focus on places such as Europa, Enceladus, and Mars, where questions about habitability demand immediate attention. But Phoebe waits with remarkable patience, preserving mysteries that may remain untouched for decades, offering future generations the chance to continue a story that has never truly reached its ending. Across the coming decades, several ambitious spacecraft will continue expanding our understanding of the outer solar system. Yet, if you follow their planned paths carefully, you discover that Phoebe remains just beyond their immediate ambitions. The moon that transformed our understanding of captured worlds still waits without a return visitor, preserving its unanswered questions beneath an ancient surface. The National Aeronautics and Space Administration plans to launch the Dragonfly mission during the year 2028, with arrival at Saturn's largest moon expected during the middle of the following decade. Dragonfly is an extraordinary rotorcraft designed to fly across Titan's varied landscapes, investigating organic chemistry and environments that may resemble conditions on the early Earth. But its remarkable capabilities are devoted entirely to Titan. Phoebe lies far beyond its planned route, remaining untouched throughout the mission. Another major expedition is already crossing interplanetary space. The European Space Agency launched the Jupiter Icy Moons Explorer during the year 2023, sending it toward Jupiter and its remarkable collection of icy worlds. Its primary destinations include Ganymede, Europa, and Callisto, each selected because of their potential subsurface oceans and geological activity. Saturn, however, is not part of that journey. Even so, scientists continue imagining what could follow the remarkable achievements of Cassini. Several mission concepts have explored the possibility of another Saturn system orbiter, equipped with modern instruments far exceeding those available during the earlier mission. Some of those studies include an additional flyby of Phoebe. Others imagine something even more ambitious, a spacecraft entering orbit around the captured moon itself. Such a mission could answer questions that remain beyond our reach today. Complete global mapping would reveal every major crater and cliff in extraordinary detail. Precision measurements of the gravitational field could expose the hidden arrangement of rock and ice inside the moon, allowing researchers to determine whether differentiation truly produced distinct internal layers. A mass spectrometer, an instrument that identifies materials by measuring the masses of their atoms and molecules, could directly analyze surface particles instead of relying only on reflected light. Careful dating of crater populations might even narrow the long-debated timing of Phoebe's capture. But another idea reaches even farther. Rather than landing, some proposed missions would collect dust drifting through the vast Phoebe ring. Those tiny grains originated from impacts across Phoebe's surface, carrying fragments of its composition throughout Saturn's outer environment. Sampling that material could provide valuable chemical information while avoiding the complexity of touching down. The engineering challenges remain formidable. Any spacecraft must first complete a journey of roughly 7 years before reaching Saturn. After arrival, matching Phoebe's distant retrograde orbit demands substantial energy because the spacecraft must reverse its direction relative to Saturn's regular moons. Even with those obstacles, Phoebe continues to stand apart as a uniquely valuable destination, an ancient survivor carrying the preserved record of the solar system's earliest history within a world already waiting inside Saturn's gravitational embrace. When we look upon Phoebe after everything we have learned, it becomes difficult to describe it as merely a moon. You begin to recognize something more profound. It is the preserved beginning of a planetary story that never reached its final chapter. Its existence reminds us that the solar system contains not only worlds that succeeded, but countless others whose growth ended before their potential could fully unfold. Planet formation has never been a certainty. It resembles a long competition unfolding across millions of years, shaped by gravity, collisions, timing, and location. Every young world gathered nearby material, while neighboring objects competed for the very same building blocks. Some grew rapidly enough to dominate their surroundings. Others remained smaller because the available material disappeared or was scattered elsewhere before enough mass could accumulate. The outcome depended as much upon circumstance as upon composition. But Phoebe began with many of the same ingredients that produced much larger worlds. It formed in the distant outer solar system from ice, rock, and carbon bearing compounds. Internal heating briefly separated portions of its interior into layers, showing that meaningful geological evolution had already begun. Material continued gathering for a time, then the environment changed. The giant planets migrated, their gravitational interactions reshaped countless orbits, and the broad reorganization of the young solar system interrupted growth across enormous distances. For worlds that happened to occupy favorable regions, accretion continued. Accretion simply means the gradual accumulation of material through repeated collisions and gravitational attraction. Those fortunate bodies eventually became planets and dwarf planets, carrying their evolution much farther. Phoebe followed the same fundamental path, yet the opportunity ended before enough material could be collected. Its development paused while larger neighbors continued advancing. The pattern appears throughout the solar system. Within the asteroid belt, Jupiter's immense gravity repeatedly disturbed growing worlds, preventing a full-sized planet from emerging. Far beyond Neptune, resonances, meaning repeating gravitational patterns, shaped the structure of the Kuiper Belt and limited where large bodies could continue growing efficiently. Between the giant planets, the centaurs wander unstable paths after being displaced from more distant origins. Each population preserves another version of interrupted planetary evolution. But Phoebe offers something exceptionally valuable. Unlike most members of those distant populations, it now circles a giant planet where a spacecraft could examine it closely. Because of that fortunate circumstance, we can study one representative in remarkable detail while gaining insight into countless similar objects that remain far beyond practical reach. Phoebe stands as a messenger for an enormous, unseen community. Perhaps that is its greatest lesson. The same physical laws that built Earth, Jupiter, and Saturn also shaped this small, captured world. Nothing about its chemistry excluded it from becoming something larger. Nothing about its earliest history guaranteed failure. Instead, its destiny emerged from changing circumstances within a dynamic young solar system where opportunity itself became one of the rarest resources, leaving Phoebe as an enduring record of a beginning that never truly had the chance to finish. Long before Earth carried oceans or living cells, before Saturn gathered its remarkable family of moons, and before any human story could begin, Phoebe was already taking shape within the same vast cloud of gas and dust that gave birth to the Sun and every major body in our solar system. As we trace that ancient beginning, you gradually realize that Phoebe's history is woven into our own in ways that reach deeper than distance or appearance. Every atom of carbon, spread across Phoebe's dark surface, shares an ancient heritage with the carbon that forms every living cell on Earth. The connection is not one of direct ancestry, nor did material travel intact from Phoebe to our planet. Instead, both originated through stellar nucleosynthesis, the process by which aging stars forge heavier elements before releasing them into space through powerful explosions and expanding stellar winds. Those long vanished stars enriched the cloud from which our solar system eventually emerged. But the similarities extend beyond individual atoms. Cassini detected complex organic compounds across Phoebe's surface, molecules belonging to the same broad chemical families identified within interstellar clouds, meteorites, comets, and many other distant environments. These discoveries reinforce an important pattern. The chemistry associated with life's ingredients appears repeatedly across the cosmos, even where life itself has never been observed. During its earliest history, Phoebe also experienced a brief interval when liquid water circulated beneath its frozen exterior. Heat released through radioactive decay temporarily warmed its interior, allowing water to interact with surrounding rock. Such interactions are known as hydrothermal chemistry, meaning chemical reactions powered by warm water moving through mineral rich material. On Earth, environments shaped by similar reactions remain among the strongest candidates for the earliest stages of biological development. The timing is equally thought provoking. Phoebe's warm interior existed during roughly the same broad era when life is believed to have emerged on the young Earth. That parallel does not suggest shared ancestry or any exchange of organisms. Instead, it highlights that comparable physical conditions arose independently in different places as the young solar system evolved. But perhaps the deeper lesson lies elsewhere. When Cassini identified organic compounds and clay minerals created through prolonged contact with liquid water, it revealed evidence that the same laws of physics and chemistry were operating across vastly different environments. Earth followed one path, Phoebe followed another. Yet, both were shaped by identical, natural principles acting under different circumstances. Seen from that perspective, the solar system becomes less like a collection of isolated worlds and more like a continuous spectrum of possibilities. Some environments remained warm enough for oceans to endure. Others froze before complex chemistry could continue. Some worlds evolved into living planets. Others preserved their earliest chapters almost unchanged. Phoebe reminds us that beneath those different outcomes lies a shared cosmic foundation, one that connects every world and every one of us to the same ancient beginning. If we widen our perspective until Saturn itself becomes only one point among many, Phoebe begins to look different. The familiar label of failed planet gradually loses its importance, replaced by a broader story about survival, transformation, and the countless paths that unfolded while the solar system was still taking shape. You are no longer looking at an exception. You are looking at one outcome among many. Every planet we know is the result of a remarkably uneven contest. During the earliest age of the solar system, countless young worlds collided, merged, fragmented, and disappeared. Earth itself grew by absorbing thousands of smaller bodies, each impact adding material while releasing enough energy to melt enormous portions of the growing planet. What appears stable today emerged from extraordinary violence spread across millions of years. Our own moon offers another reminder. The leading explanation proposes that a body about the size of Mars, known as Theia, collided with the young Earth. The impact scattered immense quantities of molten debris into orbit, where that material eventually gathered into the Moon. For Earth, the collision became another stage of growth. For Theia, it marked the end of its independent existence. Its identity dissolved into another world's history. But Phoebe followed an entirely different path. Rather than being broken apart or consumed by a larger neighbor, it endured. Its capture by Saturn altered its orbit without erasing the chemical record preserved within its ancient crust. In that sense, Phoebe retained evidence that many larger bodies permanently lost through repeated melting, differentiation, and continual geological renewal. Preservation became its remarkable fortune. As we compare these worlds, the familiar categories begin to feel less absolute. Planet, dwarf planet, moon, centaur, and Kuiper Belt object are useful names created by people to organize what we observe. They describe the destinations we recognize today. They say far less about the shared physical processes that produced those destinations in the first place. Phoebe experienced planetary accretion, meaning the gradual gathering of dust, rock, and ice through gravity into an increasingly larger body. It underwent internal heating, chemical alteration, and structural evolution before circumstances redirected its future. Its developmental story belongs to the same cosmic sequence that shaped Earth, Jupiter, and countless other worlds, even though the ending differed. But nature recognizes no formal boundaries between these labels. Gravity acts without preference. Chemistry proceeds wherever suitable conditions arise. Time reshapes every object according to the same underlying principles. Across 4,500,000,000 years, these forces produced an astonishing diversity of outcomes from remarkably similar beginnings. Viewed from that greater distance, Phoebe becomes more than an unusual moon orbiting Saturn. It stands as a preserved fragment of the early solar system itself, carrying within its frozen landscape a record of environments that vanished long ago from the warmer inner regions, allowing you to glimpse a chapter of cosmic history that almost disappeared forever. From this final vantage point, we leave Phoebe exactly where it has remained for almost the entire history of the solar system. It circles Saturn at an average distance of 12.9 million kilometers, which is about 8 million miles, following its backward path while releasing tiny grains of dust into an immense ring beyond ordinary human sight. Those particles drift onward, gradually settling onto Iapetus, influencing a neighboring world that Phoebe itself will never approach. This slow exchange has continued for about 4 billion years. During that immense span, Earth transformed beyond recognition. Continents shifted across the globe, oceans opened and disappeared. The earliest fish had yet to appear. Dinosaurs rose and vanished. Mammals spread across changing landscapes. Every chapter of familiar history unfolded while Phoebe continued its patient circuit around Saturn. Then something extraordinary happened. A small population of primates in eastern Africa gradually became a technological civilization capable of crossing the vast gulf between worlds. We learned to build machines that could survive deep space, navigate for years without repair, and arrive at distant destinations with astonishing precision. One of those machines traveled roughly 2 billion kilometers, which is about 1,243,000,000 miles, before spending only 6 hours transforming our understanding of this ancient moon. But that remarkable explorer did not endure. On September 15th, 2017, the Cassini spacecraft entered Saturn's atmosphere by deliberate design. Engineers chose that ending to eliminate any possibility that terrestrial biology might accidentally reach moons, considered scientifically valuable in the search for habitable environments. Even its final act served future discovery. Those 6 hours beside Phoebe yielded more knowledge than the previous 105 years of telescopic observation. Yet, uncertainty still surrounds many parts of its history. We continue to debate the precise moment of its capture, the structure hidden beneath its surface, and the sequence of events that shaped its remarkable journey. Each answer has revealed additional mysteries. You may find that surprising. Science often works that way. Long after every person alive today is gone, Phoebe will continue its retrograde orbit. Long after our present civilization has changed into forms we cannot imagine, it will still release dust, still contribute material to the broad ring surrounding Saturn, and still move toward the distant future shaped by gravity alone. Eventually, those same gravitational forces may pull it close enough for Saturn to tear it apart, scattering its substance into a new ring that preserves the last chapter of its extraordinary existence. But even that ending would remain part of the same uninterrupted story. Phoebe never became a planet. It became something rarer, a preserved witness to the earliest age of the solar system, carrying within its ancient rocks the chemistry that also gave rise to Earth, reminding us that our own beginning is written not only beneath our feet, but across the distant worlds that still circle the Sunday.